Hello, my name's Neil Curry and I've been asked to create a short screencast for you to talk about the golden ratio by Carol Yeager, who's pulling together a mathematics MOOC. Hopefully I don't sound too sniffy, but this is about my fourth attempt to try and create a screencast. I'm quite new to recording, but hopefully I'm going to explain to you why the golden ratio is useful both in an engineering and a photography perspective. So the golden ratio is designated by the Greek letter phi, and it's a very simple formula. It's just 1 plus root 5 divided by 2. So there we go, end of screencast. Hooray, you can get the rest of your night back. However, if you want to go into it a little bit more in depth, what you need to really do is to understand what the Fibonacci sequence is, because it's closely related. And the Fibonacci sequence, whilst it might sound quite complicated, it might even sound like a pasta dish or Manchester City's new striker, it's actually quite a simple, straightforward list of numbers, which there's a little bit of a simple rule behind them. It's very easy to mimic. Now initially it might look like a mathematician's merely coughed and sneezed all over a page and there's a big jumble of numbers, but once you start to dig a little bit deeper you'll start to realise that it's very simple. So the first number in the Fibonacci sequence is the number 1, a nice starting point. If you were to add nothing to the number 1, you also get the number 1. This is about the level of maths you're going to need. If you add 1 plus 1 you get 2. If you add 1 plus 2, you get 3. 2 plus 3 will give you 5. 3 plus 5 will give you 8. And 5 plus 8 will give you 13. I'm going to stop there because I'm stretching the full limits of my math skills, but you can see where this sequence is going. If you were to repeat that, all you need to do is to add the previous two numbers to give you the next number in the Fibonacci sequence, and that will carry on forever. Now, that's interesting, but how does that relate to the golden ratio? Well, actually, the golden ratio is closely linked to the Fibonacci sequence. If you used to divide 1 by 1, then you're going to get 1. If you divide 2 by 1, then you'll get the number 2. 3 by 2, you'll get 1.5. Now, this isn't quite the golden ratio, but if you were to carry that on through the sequence, what you do is you get this wonderful big long list of fractions, and again, because the Fibonacci sequence carries on forever, this sequence too will also carry on forever. But I'm an engineer and I get bored of looking at numbers, and the first thing I want to do is to put them on a graph to see if I can spot any patterns. And what you spot is after about the 5th or 6th term, it starts to average out around about 1.6 something. Now I'm a structural engineer, let's just talk in round numbers, try and keep it easy. And indeed when you come to the phi, when you look at the golden ratio, that also comes out to be 1.6 something. But it's an irrational number and it's also highly irrational. So the thing is, it will never converge. There is no repeatable pattern. It will just carry on forever, the same as pi. So whilst the approximations that you can see there are near enough, and they're certainly near enough for engineering purposes, it will never truly converge. But you can see that that Fibonacci sequence is also really tightly linked into the golden ratio. And when you plot them together, you can see that actually there's a pretty good fit between the two graphs there. So why is it useful? Why would we even bother learning this? Well, the human eye is naturally drawn to things which have natural beauty and things which have a nice proportional relationship based on the golden ratio. So things that are based on the golden ratio by Mother Nature we would find naturally and visually pleasing, inexplicably pleasing to look at compared to something which has a more forced geometry. And so for an example of that, I thought I'd bring in to demonstrate some of the photographs I've taken. I don't profess to be any good at photography, but I remember to take the lens cap off more often than I do leave it on, so at least I'm doing better than I used to. So one of the things that you're taught as an amateur photographer when you're starting out is how to compose images and how to make use of the rule of thirds. And effectively the rule of thirds divides the back of your camera into vertical thirds and horizontal thirds to give this little grillage that you can see on the right hand side there. And most cameras have the ability to superimpose this grillage onto the back of the viewfinder, so you can see just how easy it would be to make horizons straight, to make lampposts straight, and to get it to make sure it's not proper wonky donkey as you're trying to line it up. Keep it nice and straight. But also more important than that, it allows you to line things up at the third points. And to illustrate this, I thought what better way than trying to show you a dinosaur in an egg cup. every house should have a photograph of a dinosaur in an egg cup. There is no other way possibly I could demonstrate this. But the dinosaur in the egg cup clearly is the most visually appealing photograph I've seen in at least the last 4 seconds. It also follows the rule of thirds. So the dinosaur in the egg cup is lined up on the outer third. That negative space, that dark space on the left, is there. It sort of helps and supports the image, but I could have put it in the middle. But actually, generally, images are a lot more appealing if you follow this rule of thirds. And just to make sure I'm not lying, what we're going to do is we'll go and have a look at a few more. So I have a lovely Welshman here who is cutting some Welsh slate straight out of the mines at the bottom of Mount Snowdon. And you can see that with the rule of thirds, you can see as it's coming down, the focus there is on the equipment that he's using, the blade which he uses to cut the slate into the proper sheet sizes ready to go onto roofs of houses. Everybody loves Super Mario. My wife's Game & Watch here, again set up on 3rd points, would make a lovely eBay photo, and I hope she's not listening to this because I'm about to type in the listing for it later. But it doesn't have to be vertical alignment of thirds. You could start to look at horizontal and vertical alignment of thirds. So here you can see that the mother and daughter holding hands are roughly at the 3rd point left to right, the 3rd point up and down as well. And that makes quite a nice little photograph. It shows off a bit of sky, creates a bit of space, really sets the scene for them. And here we have Dovestones Reservoir, which is in the Peak District in the UK. And here you can see that the sky takes the top 1/3, the ground takes the bottom 1/3, but actually you've got these interesting rock formations which also fill 3rd points of the screen, and they help create that sense of drama, that sense of loftiness as we're looking down into these reservoirs which supply Manchester with some of their fresh water. But the rule of thirds is really looking nothing like the spiral which is based on the Fibonacci sequence. So how are they linked? Well, ultimately they're fairly similar as to the sweet spots where they knit over. So what you'll find now is in professional pieces of software for photography, the crop tools will have these automatic 3rd points put on, and also the ability to bring in the golden ratio. So Lightroom certainly uses these ratios to help you crop and manipulate your photographs to create these naturally pleasing ratios. And the human eye and the human brain loves looking at these natural ratios, and this is why we find quite a lot of things in nature beautiful. But these 3rd points isn't exactly the same as the Fibonacci spiral, but that's okay. We're not building a Swiss watch, we're not precision engineering anything here, we're taking photographs. We're trying to create something which has a beautiful feel to it and which is structured and is something that we could be proud to show our friends, hang on the wall, but we're not going to try and sell it for a couple of £1,000 yet. So what does that mean for us as engineers? When we're trying to design structures, when we're trying to build buildings, how does this golden ratio actually come into play? Why is it in the least bit important? Well, the Greeks, as with most branches of mathematics and geometry, got there first. The Greeks had the golden ratio phi rumbled centuries ago, and they realised that this golden ratio was a ratio which everybody just found naturally pleasing, and it occurred all over nature. So when they were constructing the Parthenon, what they did is they used the golden ratio on lots and lots of aspects of the Parthenon. But one of the easiest ones to demonstrate is the end elevation. The end view of the Parthenon is based on the golden ratio. And if you was to look at how its height to width ratio, taken on board the height to the crown of the apex to the top of the triangle there, it's roughly 1 to 1.61803. Beautifully tying in with the Fibonacci sequence there. A wonderful ratio, and it's cropping out all the way through. So even the Greeks were looking at proportioning their buildings to create them an aesthetically pleasing arrangement which has made it through as much art as it is science coming through there. And there are lots of buildings that follow these basic proportions as they come through. But the other thing associated with the phi ratio is that it ties into lots of the 3-dimensional Platonic solids based around Platonic geometry, and these take the form of the cube, the tetrahedron, octahedron, the dodecahedron, and the icosahedron. And these are some very interesting building blocks that we can use in structural engineering to start to create very interesting and very complex structures. So, for example, the icosahedron has the phi ratio is implicit in setting out the geometry of the icosahedron, but the icosahedron itself can also be used to create high-end structures such as tensegrity structures. And these sorts of structures used to be used purely for sculptural purposes, but now they're being used in medicine. And in fact, indeed, the human body is often described as a tensegrity structure. And one of the pioneers of looking at how nature and tensegrity and lightweight structures could come together was a chap called Buckminster Fuller, an incredibly clever person. And what he did was he used to go and rape and pillage nature and steal all of her wonderful ideas and look at all of the influences and the relationships between this quite sacred geometry and how it came together. And he would construct geodesic domes, which are based on natural geometries and closely linked to that phi ratio, the golden ratio. And when you look at them, you're really looking at how some of the more fundamental primitive solids will tessellate and pattern onto spherical shapes, and then you can create wonderful dome structures and even more elegant tensegrity structures and lightweight cable structures, all based upon these most primitives of solids, which are seen all through nature. And indeed, once you start to take the golden ratio, you can start to create radial plots to look at these wonderful swirly spiral patterns. And this is one that I just pulled together quite quickly in Mathematica. And you can see that this spiral pattern is quite sort of trippy. As you're looking at it, you get caught up in the swirls and the spirals, but it's very regular. It has an easily followed pattern. You can start to follow the spirals and the swirls, but then it feels familiar, and it feels familiar because the centre of sunflower seeds also follow this wonderful swirly pattern, which is based upon the golden ratio. And indeed, the Museum of Science and Industry here in Manchester had an experiment over the summer where they sent out hundreds and hundreds of sunflower seeds to get children all around growing seeds to investigate the Fibonacci sequence. It was part of their science reach out over the summer, and it went really well, and some of the results were quite spectacular. But this packing sequence, these spirals, we can start to replicate. We can start to look at how things pack, how things will come together into vessels. And here you can see some toothpicks on the left, and on the right is how I took the photograph. But naturally, these sorts of spirals just naturally want to pack. There's an organic feel to it. This is just how these spirals will ordinarily just fall out, all closely linked to the golden ratio. And you see it through biomimetics. So this is a cross section through a nautilus shell, and what you can see is as the nautilus grows, the shell starts to push around and it starts to create this spiral linked structure, which looks broadly like it might be in proportion here with the golden ratio. And biomimetics is a huge research area where at the moment my research background is we're looking at deployable structures. I look at deployable structures for disaster relief, and one of the things that I have a couple of students looking at is biomimetics, looking at how mechanisms will fold. One lady in particular is looking at beetle wings and how those mechanisms for beetle wings will fold, how to scale them up and make them cover large open spaces like football stadiums, baseball stadiums, any open plan roof, and also even how to make articulated facades that will follow these folding rules from biomimetics and look at the ratios and the presentation of them so that it can create some natural shading onto the facades. And hopefully, as that work progresses, I'll be able to show you some of the exciting animations that are coming out of that. So I hope you found that useful. I hope Carol's pleased with me. There's no invoice to come from this, it's completely free. I'm doing it to hopefully try and boost the MOOC and let you see how the golden ratio is used in engineering and in photography. I hope you enjoyed. Bye bye.